structured parallel programming, and I'll talk a bit about TBB, to give a perspective on programming models and programming, kind of stepping back. So structured parallel programming, one of the things that really hit me looking through programming books for HPC somewhere around a decade ago is that more than half the book is usually dedicated to talking about computer architecture. And that's pretty amazing, because you can pick up a book on C or C++ or Java, and very little of the book, if any, talks about computer architecture. But once we get to HPC, we spend more time talking about computer architecture than programming techniques. And that kind of gives us a tunnel vision that I sometimes like to try to break. And so one of the ways we did that is Mike McCool and Arch Robson and myself put together a book on structured parallel programming. It's used in some colleges now. And we focused on patterns. Now, if you know what a pattern is, if you've seen people who go nuts over patterns, there are conferences on programming patterns, and there are books this thick, one of them written by a colleague of mine, Tim Mattson. And you know, it's good put you to sleep material, in my opinion, because they want to make sure that they have a pattern for everything. I look at it from a more practical standpoint. I want to talk about patterns that work, patterns that we know how to make run in parallel, and so forth. And I think when you're learning programming, you learn things like stacks and queues and linked lists. And we teach those because those are data structures that we found to be useful. And it's kind of cool if I can say, well, I'm using a LIFO queue or a FIFO queue. You and I should know what each other is talking about. Well, when we get into parallel programming, I'd like to be able to talk about map and reduce and stencil operations. There were a couple mentioned yesterday by Pete, like adaptive mesh refinement or particle in a cell. Anyways, there are different patterns we should learn. So if my intent with a very short overview of this is to kind of tickle your fancy to say, hey, there are people who have studied patterns, and learning a little bit about that and understanding why people talk about patterns can be incredibly useful, because a pattern may be part of the key, by the way, to getting performance portability, is to map your problem onto a pattern that people have figured out how to port across different architectures. Stencils being one of my favorite. And so there's lots and lots of patterns. If you get our book, there's lots of patterns we cover. There's other books. There's lots of conference papers about patterns. And patterns are really best practices. And if you organize your program around using a pattern, not only can you talk about it with other people more easily, but you can also benefit from other people finding ways to map these patterns onto different architectures. So I think as we look at the evolution of applications, we'll see more strongly different domains standardizing on how they solve problems and how they approach it. And that gives the architectures a chance to align to perform well on these patterns, libraries to align, all sorts of different things. Anyways, if we look at really simple patterns, if you look at sequential, you know, you could just have a sequential pattern. You do this function, then this one, then that one. You know, superscalar, this is how we draw that some of the things can happen in parallel. You know, it's a flow chart, but it's you can start to set up different patterns, and you can have iterations, a simple serial with a while loop, or you could do a counted loop. These are different patterns that are familiar to all of us and are coded into our programming languages, burned into our minds. This one, the for loop really frustrates me, especially as a compiler writer, because a for loop says do iteration 0, and then do iteration 1 and 2 and 3 in that order. And then you frustrate the compiler trying to figure out whether it can do it in parallel. And I think I call this a serial trap in the book. It's the programming language was actually sets us up for a difficulty making it run in parallel, because the pattern that you used as a programmer here was to say, do this, but do it sequentially. Now, you know, if you use something like do concurrent in Fortran or some form of for all or parallel for, then you as a programmer are saying, hey, run this in parallel. But here, you as a programmer are saying, run it in serial. And then you're frustrated it doesn't run faster on a parallel machine. So our programming languages have some catching up to do. But if you start to recognize even a simple thing like a for loop as a pattern, and that you've actually maybe not asked for what you wanted or not given the compiler enough flexibility. So we can get things like a map operation. I mean, this is what makes Google search engines run so well, is the Google folks are, you know, they're not allowed to write anything that can't be done in a map operation. That's pretty close to true. Because map is beautiful. You've got a bunch of totally independent operations. How many cores do I have? Let's go. Now, that's great. Use map all the time that you can. In fact, I'm a big believer in teaching parallel programming and starting with something that works really well with map and speeds up fantastically, right? And then introducing the headache that, you know, map can't solve everything. Of course, there are reductions, and understanding when you're doing a reduction and allowing yourself to use reduction operators that may be optimized, like an OpenMP or other constructs, is incredibly important. Of course, reductions can be done in parallel as well. Scan is not as well widely used, but worth understanding. Scan is an operation that typically isn't, a lot of people think can't be done in parallel, but there are actually solutions. So understanding a lot of the patterns that are out there and available to us is great. Now, I think the stencil, when we were working on the book, I remember stencil was like a subchapter of a subchapter, and I don't know why it didn't dawn on us sooner, but I said, no, I like stencils a lot. We made it a chapter, because stencils are incredibly important. Stencils have gotten a lot of conversation in the industry as well, because stencils usually have a halo around them. And there have been some really great papers published about the trade-off between the size of the halo and the performance, because the bigger you make the halo, the more redundant calculations you do on each node, but the less communication you do. And so if you understand that, and you understand that different architectures give different trade-offs, then the ideal thing to do with a stencil operation is to code it in a way that's parameterized with the size of the halo. Don't hard code it to have one, you know, set of numbers as your halo, or 3 sets. Parameterize it, because if you parameterize it, if you know you're committed to using stencil operations, you parameterize it, you change the size of the halo, you are increasing the computation when you make it bigger on each node, but you're decreasing the communication. And this is a brilliant way to get performance portability, because I consider a program that doesn't need to be changed, that has parameters like that, to be very performance portable. You just tweak the parameters. So again, a benefit of knowing these patterns and knowing that you can move your code or part of your code to use this pattern is that there's a lot of, there are a lot of other people using that pattern, developing tools for it, libraries for it, so forth. So if patterns aren't part of your vocabulary, just take it as me encouraging that. The final pattern I'll mention is pipelines. And this one's going to come back to us now with FPGAs. I remember talking to Herb Sutter a long time ago about pipelines, and he said, pipelines aren't parallel. And I said, oh no, you don't get it. Each stage of a pipeline might be parallel, and then the pipeline itself is, has a flow through it. Pipelines are a really incredible, rich area for running in parallel. And again, if you have dependencies, if you have a workflow, but you are worried about getting throughput, thinking about a problem in terms of a pipeline can be incredibly helpful. And then each of the, like I said, each of the stages of the pipeline may be an operation you can run in parallel in different ways. There's nothing against doing that, a lot of data processing. But I think we're going to see pipelines have a big resurgence in interest because of FPGAs. Of course, we all know fork join. But anyways, the takeaway here is if you've heard about patterns but are scared away, or if you've never heard of them before, they should be part of your vocabulary. And I have occasionally, we've done an all-day tutorial at Supercomputing on patterns. I don't know that we'll ever do that again. But as you look at applications moving forward, there's work out of UC Berkeley on, they call them dwarves, and then they call them motifs. Again, the same idea is, what are recurring themes in the applications the way we develop them, and can we start building a vocabulary about certain things that we're doing, and then talk about how to make those run well in parallel, develop frameworks, language extensions, libraries to do that. Being in tune with the vocabulary and the different patterns people are working on is a great way to align, and probably ultimately the key to performance portability, or some aspect of it, is to align work around patterns. Because a stencil can implement many, many different things, so you're not just beholden to one particular type of code, but the stencil pattern may be used by lots of different application types. Now, I wanted to talk a little bit about TBB, and the reason I want to talk about it is I want to illustrate some concepts about parallel abstractions. So I will maintain that the more abstract a method of implementing parallelism is, the more portable it becomes. Now, the challenge is, the more abstract it is, often the harder it is to map it efficiently to the hardware. Well, harder and easier. The abstraction, if it's done properly, leaves a lot of flexibility for an implementer of a library or compiler to give you the parallelism. But on the other hand, if the library or compiler fails to give you the parallelism, it gives you very little flexibility as a developer to fix that. You can submit a bug report and wait. And this is the frustration of being a programmer, is if you get really down and dirty in programming machine language, or really close to the metal, you're in more control, but then your application isn't as portable. If you decide to trust a compiler or a library, you have less control. You will be more portable, but you're more reliant on others. But let me talk a little about that, because one of the key things, and I think we've done pretty well in the last 10 years of shifting this, is you should be programming in tasks, not threads. And the way I would describe it is this. Your job as a programmer is to figure out a lot of things that we can do in parallel, but you should not be the person mapping the task onto the actual hardware. Now, this is the toughest audience to sell on this at all is HPC, with affinities and mapping and pinning things down. But what I'm saying is you would not want to write a program for a quad-core processor and have hard-coded into your code 4 everywhere. When you get an 8-core processor, you've got a problem. The other thing is nested parallelism turns out to be very difficult if you hard code it, because if you divide your program up into 4 parts, but it turns out they're not even, how do you map stuff around? So TBB has been extremely successful in the C++ arena. We introduced TBB about 10 years ago. This was my second book. This is how I got into the book writing thing. The first book convinced me never to write another book. The second book that should have been written was the book on TBB, and I tried to convince the architects and the people that were doing it to write the book, and they said they were too busy. But I was too excited about TBB, so I wrote this book, and then I couldn't stop. So TBB is C++, and it implements what fundamentally we call a task stealing scheduler. And what that means is, if you were to have a lot of work to do, you could come up with a bunch of tasks and put all of them in a queue. And every core on your machine could go to that queue and grab a task item out of it. It's a work jar. And the problem is if you have one work jar and everybody's trying to grab at it, it becomes a global bottleneck. a ridiculous global bottleneck. So everybody's waiting longer to get their task assigned to them than they are doing the task. So what MIT researchers came up with under Charles Lyserson back in the mid-90s was this idea of basically a distributed queue. And it means that work gets, there's probably a queue for every node or a queue for every core. And when the core runs out of work, it grabs the next item out of its own queue. And then if its queue runs dry, then it goes and tries to steal from other queues. A pretty simple concept. It alleviates the global bottleneck. Now, if you were to write an application and then write the application to do all that, that'd be pretty hairy. So what TBB does is says, hey, you write your application to create task. We wrote the stuff that will manage all the queues underneath. And it's open source, and it's been extremely popular. And it's got a bunch of things. I like to describe TBB as trying to plug all the holes in C++ for parallelism. And so hopefully over time, many of the things will actually become part of the C++ standard. In fact, C++ 11 implemented quite a few of these things that were uniquely in TBB. And so over time, TBB should probably go back to being a task-stealing scheduler with some algorithms on top of it. And the rest of the stuff should probably become part of C++, like standard atomics and locks that work on every operating system. That's something that we introduced in TBB and have advocated for in C++ standard. That belongs in the standard. But things like the task scheduler and generic algorithms are part of TBB. So anyways, TBB is not heavily used in HPC for two reasons. One, most of HPC is not in C++. TBB is a template library. So it's definitely C++. And the other is TBB is very oriented towards unstructured problems that don't map very, very easily to a set number of cores. So a lot of scientific applications are written so that the partitioning is strongly understood in the program. And that probably, that served HPC applications well for a while. But as we see more and more unstructured problems written in C++, we see more and more use in HPC. It's much more popular in the digital media industry. It pretty much dominates Hollywood for all the animation. Companies like Pixar and DreamWorks use TBB for their parallelism exclusively, extremely well. Anyways, so one of the things TBB does really, really well is nested parallelism, meaning I may be running a for loop, but one of the iterations discovers massive amounts of parallelism, and what happens is that parallelism gets dumped on a queue, and it can be stolen, so it evens out across the cores. And this is really helpful. OpenMP sucks at this. OpenMP was designed to parallelize once well, and nested parallelism is horrible in OpenMP. Now, this debate, of course, OpenMP understands this, the OpenMP committee, the users. And there's a new thing called hot teams. And I wanted to finish by describing this, because if you're using OpenMP and you're seeing imbalance, and this is getting to be more and more important today, it's important to know that these language standards are evolving. And when you see something like TBB take off and you look at why, then the question is, will that be adopted in some of the other things? So if you're a C or Fortran programmer, what about nested parallelism for me? Well, hot teams is a feature of Intel compilers. It actually doesn't change the standard. So I think we'll see other compilers for other vendors support this in time or something like it. But normally, if you are running an OpenMP application and you say you're running 4 tasks or four team members, each one of them will create 4 more when you go one more level of nesting. So most OpenMP implementations, if you nest OpenMP, if you call OpenMP while you're already in OpenMP, won't create anything else, because it actually creates another set of stacks, another set of members. It can be explosive. But every OpenMP implementation out there, when you start it, it goes and gets a set of processes from the operating system, which is very expensive, and it keeps them, even if you come in and out of OpenMP. But every OpenMP implementation I know of out in the world, if you go one more level and you've turned it on, it will create those processes, but it gives them back. So the second level of OpenMP is very, very high latency, very high overhead. And so nesting OpenMP, a lot of people will turn on nesting, try it, their program slows down, they turn it back off, and they go do something else. And what they didn't understand was the implementation itself was doing something that seems kind of foolish. It was grabbing those processes and then giving them back each time you went in and out of the second level. So all that Intel has done in their compiler is allowed nesting to be turned for some variables to be set. Let me see. You can set some environment variables that puts it in a hot team mode and tells the runtime, don't give those back to the operating system if I go into a second level, come in and out. I know what I'm doing. I'm not worried that you need to give them back during the lifetime of the program. The reason the runtimes default to that is they're afraid that you do some nesting, that it's created all this extra footprint, and that later in your program will blow up because it's got that extra footprint that you're not using. But if you're actually going to use it, you turn it on and leave it on. So I look at this as a fascinating evolution of, you've got on one hand a debate going on in the C++ community, standardizing with TBB, heavily using nesting. By the way, the reason nesting didn't matter that much when OpenMP was invented in 96 or 97 was that nodes weren't very fat. Nodes have gotten fat, and so a lot of the node programming is done using OpenMP, and there's so much parallelism there that OpenMP nesting starts to become important. And nesting in OpenMP needs to get better. So for several years, Intel supported this, and there are a couple of examples in a couple of the Pearls books, chapters 18 and 10 in the last book. But there are some articles online about this and hot teams. So the reason I brought it up is unfortunately, when you're using something like OpenMP that was originally designed in 97, and it has a strong tendency to want to have good legacy support. That's why your programs don't break all the time. It does carry along some baggage that you need to get educated about. And with OpenMP, the number one thing I'd encourage you to get educated about is nesting and this hot nesting capability. And I think you'll find with a lot of applications that use OpenMP, you may have the opportunity to play with enabling an extra level of nesting that'll give you an even more even balance of your workload on your node. Read that as use your parallelism better, and it's something to play with. Now after lunch I'll talk about vectorization and some features in OpenMP for that as well that are worth looking at, that are new as well, trying to take advantage of new architectural features. But the nesting is really important. I think with the fat nodes, if you don't understand how to get nested parallelism, you should. OpenMP, experiment with turning on nesting. There's lots and lots of books out there and stuff on OpenMP that'll tell you don't use nesting. It has explosive growth, it'll blow things up, it's never worthwhile. Just keep in mind those were written over the last decade or two when it didn't matter, and it's changing. And I think we're seeing a lot of success with using nesting now, even though the common wisdom is don't. And that's because architectures and machine designs have changed enough that it's actually flipped the bid on that. So with that, we should, I'll take one or two questions if there are, or we definitely can do that after.
One of the comments in the book is, in case your application isn't NUMA aware, or it's not NUMA friendly, then you should, then probably the quadrant mode would work better than the SNC4. Why so? I mean, shouldn't the worst case for SNC4 be the quadrant?
So let's, so let me parse that. Yeah, in the book, I say that if you have a program that's not NUMA aware, run it in quadrant mode instead of SNC4. So let me parse that a little. What I mean by that is if you're running a program that's not NUMA-aware on all 72 cores, on all the cores, then the program probably isn't optimized understanding that some memory is close and some is far. And so if you are randomly touching memory, you're better off in the quadrant mode because the time to all the memory is the same. If you go in SNC4 mode, a quarter of the memory is faster and 3/4 is slower. And the math works out such that if you're randomly touching memory all over, 3/4 is slower, 1/4 is faster, it actually turns out to be slower overall. A NUMA-aware application would localize your accesses to the near memory and would get a performance boost. A non-NUMA-aware wouldn't. Again, I'm talking about if you're trying to run an application across all the cores. I think the way most people will run applications on quadrants or on quarters will be to divide it up into MPI ranks. But you can also write NUMA-aware applications as well. Does that make sense?
Yeah. And maybe I should ask, I have one more question. Maybe I should ask this later, but is vectorization, like how critical is it for utilizing the high bandwidth memory, like the entire bandwidth of the high bandwidth memory?
It's incredibly important, and I'll talk about that after lunch, but that's a very good thing. Vectorization, if you don't vectorize code and you're fetching one data element at a time, you're going to become CPU bound because you're using more instructions. And what you really want to do, if at all possible, is become bandwidth bound, right? So you can use the bandwidth in the machine. It's funny, people talk about whether machines are balanced or not. It's like, well, your objective always is to reverse the balance of your application, right? If you're bandwidth bound, you want to figure out how to reduce your memory usage so you become CPU bound. As soon as you're CPU bound, you should try to go back to bandwidth by reducing CPU. That's what our game is as an application developer. So the bandwidth, to take advantage of the bandwidth of that, you need to become bandwidth bound. You need to be pumping it, so you need to make sure you aren't doing so many computations that you can't be issuing enough requests to memory. Because you want to use the full bandwidth in the machine if possible. So yeah, vector instructions are the way that you're going to get that. If you're not using vector instructions, I doubt you'll be able to hit the bandwidth of the machine anywhere near as easily.